Okay, so in this part of the course, we're going to be talking about energy and the work energy theorem, which is, I would argue, one of the most, if not the most important part of physics, since this will continue to come up over and over and over and again. Physics 2 will have a bit of work energy things in there, definitely in your further physics classes, and especially if you're in engineering, you'll see this a lot in engineering. Not so much for the 2053 people, you won't see too much more of work energy, but this is arguably one of the most important topics inside of Physics 1. So, from above, we know that work is this thing that tells me how much energy it takes to go from one place to another, as we discussed earlier. And since they're essentially the same thing, work is energy, there's a theorem called the work energy theorem, which relates the two using a very nifty formula that we'll get to soon. But first thing we want to talk about is the differences between what a conservative force is and what non-conservative forces are. So, conservative forces, conservative work. If you have some plane like this, let's say that this is the ground down here, and we drop a ball from up here. It does not matter how the ball travels. The conservative work, which is the gravitational work, doesn't matter how the ball got to wherever it got to. It could go in a path something crazy like this, but if it ends up down here, the only thing that matters is this change in height, the initial position and the final position. Nothing else matters, and that's the basis of what a conservative work does. It means it's not path dependent. It doesn't matter how it got from this position to this position. It just did, and the only thing you need to care about is that displacement that it covered. Now, non-conservative work means it is path dependent. So it does matter if it takes a really crazy looking path from here to here. And if it does all this has to be factored in. It's not just displacement anymore. It is the total path length. Everything in that path does count towards the work done. That's what non-conservative work does. Now, if you're wondering about the derivations behind conservative and non-conservative vector fields, this comes from Calculus 3. And it's essentially, there's a way to prove if the vector field is conservative or not using gradients partial derivatives. But we're not going to do that because this is Physics 1 and it's not necessary. All you have to know is that conservative work and conservative forces are springs and gravity. Nothing else. If you see a spring, that is a conservative force. If you see gravity, that is conservative work. Non-conservative forces in Physics A are anything other than those two. Mainly friction. Friction is the biggest one. If you see friction, you should always know that that is non-conservative. Always. Also, if you see just random forces, just any random force, someone put a push, that is also a non-conservative force. So let's get into the work energy theorem. Well, conservative work is defined as the negative change in potential energy. The net work, the total work, is defined as the change in kinetic energy. So if you have W net, you can say that W net is equal to the conservative work plus the non-conservative work. You can then substitute in this negative delta U into here and move that over, and you have that work non-conservative is equal to the change in kinetic energy plus the change in potential energy. This is also known as the total mechanical energy. So you can say that WNC, the non-conservative work, is equal to the total change in mechanical energy. So let's talk about we talked about conservative and non-conservative things, right? So these are the conservative works right here. You have gravity, which is this is essentially a new thing called potential energy, which is how close is an object to being able to move, right? So for potential energy, you have a cliff like this. The higher this is from above the ground, the more potential energy it is, because it's only defined as being the mass of the object, the gravitational constant, and the height above ground. So you go up here, it has more potential energy. You go up here, it has even more potential energy. Now, spring energy is defined as 1/2 kx squared. So if you have a spring like this, and you just place it back to here, you just place it some distance, we'll call this x, that's all that matters inside of spring energy, is how far back do you displace that spring, how much pressure do you apply on that spring. This is also potential energy. Now, there's something called kinetic energy. Kinetic energy is no longer a type of potential energy. This is now what happens once potential energy is released and this object starts to go in motion. So if this thing has some velocity, if it ever has a velocity, it has kinetic energy. So let's do this question. We have a block. We'll say this block is all the way up here on the very top of this thing with some height theta. We'll say that this spring has a constant k. And we want to know how far back. So this block is essentially going to slide down this hill, and it's going to come across this. It's going to hit this spring, and then it's going to come back some distance, right? We want to know how far that distance will be based off of the variables that we have. And we'll say that there is some friction here. We'll say this is frictionless, this ramp is frictionless, but we'll say this has some coefficient of kinetic friction. So how do we do this? Well, let's start with the formula. The non-conservative work is equal to the change in mechanical energy, where change in mechanical energy is equal to the change in potential energy plus the change in kinetic energy. Now, what you want to do is you want to think of this like a video, right? So, in the initial frame, what's going on? Before this thing is moving, when it's right here, what is going on? What does this thing have? This thing has some sort of potential. Oh, and one more thing before we start evaluating this. So, typically, right, in kinetics, we said we have to draw a free body diagram, and we have to do our sums of forces equation and our axis. There's one more thing you have to do in work energy, which is define a 0 point. I'm going to define my 0 point as the ground. And what does that mean? It just means that here is where there's no potential energy. If an object is on the ground, it has no potential energy. Anything above that, it has potential energy. So you just have to say, that's my 0. So my 0 is the ground. So we have non-conservative work is equal to change in potential energy plus the change in kinetic energy. And what we want to do is just think of this like a video. We have frame 1 here, and we want to know what happens in whatever frame it's going to end up here. Realistically, you want to break this down into about 3 different motions. You want to break it down the motion from when it starts up here to when it ends down here. You want to do another one from when it's here to when it hits the spring, another one during the compression of the spring, and then another one after the compression of the spring. That's what you want to do. You could also do this all one stroke, but that's there's a lot of not extra math, but that's just a lot of math. There's a lot of ways to make mistakes with that. So I would just advise to do it in one or at multiple different positions. So we'll go ahead and do this. So we start up here. Is there any non-conservative work? This is the first thing we want to ask ourselves. Is there any friction on this ramp? Is there any forces pushing on this box? The answer is no. So we know that this non-conservative work is 0. Is there any potential energy on this box? Yes, there is potential energy initially, right? So this delta U is U final minus U initial plus K final minus K initial. Is there any U final? No, because it's going to end up right here at the 0 point, right? So there's not going to be any potential energy once it gets to that bottom. So it's going to be 0 minus, is there any initial potential energy? Yes. There's this height, right? This box is above the ground, so there is a potential energy, which is minus mgh, right? So it's above some mgh there. Plus, is there any final kinetic energy? Yes, this will have 1/2 mv squared. Is there any initial kinetic energy? No, it's starting at rest, so this is plus 0. So, doing some rearrangements, we have mgh is equal to 1/2 mv squared. We can cancel our m's. We have gh equals 1/2 v squared. What we really want to find is the velocity at this point, so that way we can calculate how far it's going to travel to hit that spring, right? So, v squared, we'll say 2gh, the square root of that is equal to our velocity at this bottom point. Okay. Now let's redraw this picture, but with the block now at the bottom, right? So the block is now here. It's hit the bottom of that spring. It has some initial velocity v, right? Because we just said it has that initial velocity v now. That's at that point. So, let's see. It has this initial velocity v. There's some coefficient of kinetic friction. We want to know, and this is some length d to the beginning of the spring. So we want to know how much, what velocity does it keep when it actually starts compressing that spring. So let's do that. So we go again. W and C is equal to delta E. Is there any non-conservative work? We want to ask ourselves, is there friction? There is friction. So we have to expand this non-conservative work term into the integral of f dot dx. Or, if you're in 2053, this would just be force distance cosine theta is equal to the change in mechanical energy. Is there any potential energy initially? No, there is no potential energy initially. Is there any final potential energy? Yeah, we'll go ahead and include this in the motion. So there is going to be final potential energy, which is going to be negative 1/2 kx squared, because it's ui minus uf, or sorry, this would be positive 1/2 kx squared, because it's uf minus ui. So 1/2 kx squared. Is there any initial kinetic energy? Yes. Is there any final kinetic energy? Probably. So we're going to keep that in there. No, sorry, there would be no final kinetic energy once it compresses that spring entirely. So this would be 0 minus 1/2 mv squared. Because if we think about this, right, this box is going to keep traveling. It's going to keep traveling. It's going to keep traveling. It's going to hit this spring. It's going to slow it down until it comes to a stop, right? It's going to come to a stop when it's at that full compressed motion, when it has that full 1/2 kx squared. So what I really want to know is probably, let's see. We don't really need to solve for too much here except the compression of that spring, because that compression is going to tell us exactly how far, that's going to tell us how far it's going to shoot back when it actually makes the motion that comes back this way. So we'll solve for that. So we'll say fd cosine theta plus 1/2 mv squared is equal to 1/2 kx squared. We cannot cancel anything, but I can multiply this by 2. 2fd cosine theta plus mv squared is equal to kx squared. We'll divide by k, so we have 2fd cosine theta plus mv squared divided by k, and the square root of that is equal to x. So now we have this x. I'm going to expand this a little bit more because we have that velocity as just being the square root of 2gh, right? So we'll have the square root of 2fd cosine theta plus m 2gh, because I can get rid of the square root since it's squared anyway, divided by k. This is equal to our compression distance. Now we can analyze the motion of it being fully compressed. So I'll draw another picture. This is, this has now been compressed some distance x, and it's now still on this friction full surface, and it's going to go back some distance d. It's going to travel some distance again, some new distance d. So let's see. We want to probably have this compression distance. So let's again write down our formula. W and C is equal to delta E. Delta E. Is there any friction force? Is there any non-conservative work? Yes. So we know this is going to be F d cosine theta. And one thing to note, that this F d cosine theta will likely become negative inside of, because the friction force is pulling against it, so that cosine will be 180. But this is a function. We're making this some function. This would be x as a function of the angle, as a function of the height, and as a function of... And this force, actually, we can also expand this as well to be the force of friction, which is just 2 times mu k n d cosine theta. So as a function of the height, and then that n can also be expanded again. It's just be mg. So it'd be 2 mu k mg d cosine theta. So there we go. So this is the function. Let's see this here. So we have f d cosine theta is equal to the change in energy. So this is still mu k m g cosine theta, mu k, g d cosine theta. That's equal to. Is there any final potential energy? No. Is there any initial potential energy? Yes. So we have negative 1/2 kx squared. We have that x. Now, we do know that there is going to be some 1/2 mv squared at the very. Actually, there's going to be no 1/2 mv squared because we want to know how far it's going to continue to travel in this direction. So it'll literally just be this because we know it's going to come to a start. So there is no kinetic energy, and there is no kinetic energy initially. So now we just want to solve for this new d. I'm going to plug in. Actually, we'll just solve for d off the bat. So we'll have d is equal to negative 1/2 kx squared. Divide this by mu k mg cosine theta, and I'll plug in this nasty expression into that x. So if d is equal to negative 1/2 kx squared, d is equal to, or actually, we'll just leave it like this for now, and I'll leave it as an exercise for you guys to plug it back in. And yep, so that would be the end of this video on how to solve for things using the work energy theorem. Essentially, to recap, just break it down into small little like videos in your head. You have it going from here to traveling down to here, and then you need to make another motion from here to here, and then back again from here to here. So you want to do 3 different times to get it all complete. Alright, and that's the end of the work energy theorem video. Thank you for watching.